ஓகே. அது காமனா தான் ரெக்கார்ட் ஆகுது போல.
ஆமா ரெக்கார்ட் ஆக ஆரம்பிச்சிருது. 9:22 காமிக்கிறது லெஃப்ட்ல.
ஆமா, after the meeting it will be visible for everyone.
Fine then.
Okay. So I'll just start. Hi guys, எல்லாரும். தன்யா, ஃபாசில், மைத்ரேயன், பிரியதர்ஷினி, நாகாதர்ஷன், எவ்வளோ 6 பேரா மொத்தமோ? ஆமா. So somebody messaged me. Could you please send the meeting link? I'm not able to see anything the meeting oriented from the Teams link ன்னு ஒருத்தன் கேட்டிருக்கான் வாட்ஸ்அப்ல. How do I share the meeting link? Actually, I have no idea how to share the meeting link. Okay, I'll just start அப்போ. So basically, this is like unit 3 guys in the combinatorics, groups, fields, அதெல்லாம். So first we'll look into the algebraic structures. That is this page from page 5. Yeah, this is Udhaya's notes. I'm very happy that he sent to his notes. So using that, I'll teach. So okay, for me, I preferably understand if everything is there in one page. So I just made a small like cheat sheet for everything. So I made this using LaTeX. I think you would find this useful too. By the way, can you hear me now? People இருக்காங்கல்ல?
Yeah, we can hear you.
Yeah. So let's just start with groupoid. Groupoid is nothing but a set of numbers. Take for example 1, 2, 3 or 4, 5, 6. Just a set G with property only being closure. For example, take again real integers. Closure being, rather if you take A and B belonging to set and apply an operation, it will again be back in the set. So Z minus means take the integers and minus operation. We have 1, 2. 1 minus 2 will also be minus 1, which is another integer. So very simple. Groupoid is nothing but a set with closure. So in this set, like semigroup, monoid group, each one will build on the previous one. So பாத்தீங்கன்னா இப்போ semigroup would be groupoid plus something. Monoid will be semigroup another thing. So semigroup here is groupoid plus associative property. So it's closure and associative. Example here is n plus. So n here is natural number and plus is the addition operation. So Second, so take any two random natural numbers. If you add them, it will again be a natural number. 1 plus 2 is 3 natural. An associative means, so 1 plus 2 plus 3, the order which, of addition does not matter here. So we can do 1 plus 2 first or 2 plus 3 first. Again, we'll get the same thing. So next, wait, we'll just go to this. Yeah. Okay, he starts from group here. He starts group called semi-group. So okay, again, monoid here is semi-group with identity operator. So it will be closure, associative, and identity operator. So here you can say existence of an identity. So identity means like you have an operation plus. So if you do that operation on something, it will effectively amount to nothing. So 1 plus 0 will be 1. So that is the existence of an identity. And you can see here is n0. That is natural numbers with 0 in that. Plus. So effectively whole number set. It should not be n0. It should be w there. So monoid is semi-group plus identity operation. Let's just take group next. So group would be monoid having inverse operation. Yes, here. So here you can see that the group has closure, associative, identity, and inverse. So inverse means like A, any object, and A star, that is another object. If we do that operation, it will give you the identity operator. Let's just take this example, group Z plus. So here, inverse exists because you have 1 and then minus 1. Yeah, you have 1 and then minus 1. So if you add both of those, 0, which is the identity operator. So group has closure, associative, identity, and inverse. So in group, there's another thing called as abelian group, which is nothing but group which has commutative operations possible. So you can just go here. Yeah. So group has commutative operations possible. So commutativity means that your order does not matter here. So you can do A plus B or B plus A, both will result in the same thing. Here they have used star, which is in placeholder for any operation. So again, that's also Z plus. So cyclic group. So cyclic group is an interesting thing. So imagine a group which is created by just one element. Like, right? Oh, wait, I can write here. Yeah. So, oh, wait. Second. How do I start this? Yeah, so cyclic group, let's just go. For example, you have like a random variable, like you just take 2. 2 power n. So 2 power n can the number 2 and then power n like 1, 2, 3, 2 power 1, 2 power 2, 2 power 3. That will give you a group that's generated by just 2. So that is one example of a cyclic group. It again follows all the principles of a group, but it's generated by one element. Again here, Zn means, so a set of group, Zn means set of modulus n. So 1, 2. So this is Z4. So effectively modulus 4. Any whole number modulus 4. So that's a cyclic group. So next, ring. So till now we saw groupoid, semigroup, monoid group, abelian group, and cyclic group. All these follow one operation, that is plus or minus. It should be only one operation. But ring and field, they can have two. They're defined by two operations. For example, ring here just says that it's two operations, plus and multiplication. So again, the operation here is defined. It can't be a random operation. It's plus and multiplication. Under plus, it's an abelian group. Under multiplication, it's associative and distributive. But ring does not necessarily need to have an inverse. Just go to rings here. Ring inverse. Okay, let's just look at this. So ring is not necessarily required to have an inverse. For example, take real numbers. Take all the integers. So let's just take 2. 2's inverse, multiplicative inverse is 1 by 2. 8. Yeah. So let's just take 2 here. Inverse of 2 is 1 by 2 when it comes to multiplication. But that cannot be there in a ring because ring does not necessarily need to be like inverse in multiplication. 1 by 2 does not come under integers. It comes under rational numbers. So field is like nothing but ring plus inverse. So inverse exists for all things except 0 in a field. So field would be a set of all rational numbers instead of set of all real numbers. Let's bring another thing here. Let's take a pen. Okay, so let's just move to homomorphism and isomorphism next. So homomorphism is like essentially means that how similar are two structures. We have one group which is yeah, we have one group which is A and has operation star. Another group which is B and has operation O, for example. That's not 0, that should be O. I am writing with my mouse, so it's not mouse, touchpad, so it will be horrible there. So homomorphism means that structure of this one and this one should be preserved in operation. So take, for example, here f of A into B. So function is effectively from A to B. So if f of A into B into here is the operation, that is operation from the domain, which is A set A, that is into, equal to f of A into f of B. Then it's homomorphism. So essentially the structure is preserved here. So example given here is f of x equal to x mod n. So just take okay 2 1 x mod n. So we can have mod 4 like what we saw above. Mod 4. Take the two numbers 2 and 3. So f of a into b, that is f of 6, would be mod 4 means it will be 2. And f of a into f of b. So if f of a is 2, f of b is 2, We multiply it, we get 6. Again, the whole should be mod, it will be back to 2. So homomorphism is essentially preserving the structure. So isomorphism is nothing but, in case of homomorphism, the function f should be a bijective function. So bijection here means one to one and onto. So homomorphism is preserving structure when two functions are there, and isomorphism is homomorphism that is bijective in nature. Just a second. How do I clear this annotations? Okay, so now here is that one-line intuition I just told. So homomorphism is structure preserving maps, and isomorphism is preserving the exact perfect match. So next, let's just go to subgroup, coset, and Lagrange's theorem. So subgroup is essentially nothing but a group, which is a subset of a group. So just take here G. So here G is a group. G is a group with operation. Let's just take multiplication. So for H to be a subgroup, H should also have the same operation, that is multiplication operation, and H should be a subset of G, and H should be a group. So if H is a subset of G, follows the same operation, and it's a group in itself, so it will be a subgroup of G, specific to G. So here, the example here is, the group here is Z comma plus, that is all integers, and the operation is addition. The subgroup here is 2Z, that is a set of all even numbers. Set of all even numbers, it follows the properties of being subgroup of all integers. It follows its own set of group properties, that's addition, commutativity, closure, every property, and it follows the same plus. So 2Z would be a subset of Z. Next, okay, cosets. So cosets are relations of subgroups. So take the same subgroup H here. H is a set of all even numbers. 2, 4, and so on. So we need a coset of H. So for a set to be a coset of H, the coset should have the same size as H, and it should be a subgroup of the same group, and it should not have any overlapping numbers. So here what they're doing is GH. So here G is a random number and the star is an operation. Here we're using G as 1 and the operation as plus. So essentially what is happening here is every item in the subgroup 2z, they're just shifting by 1. So set of all even numbers becomes set of all odd numbers. That's it. So both are subgroups of set of all real numbers of all integers. Both of them are subgroups of integers. Both of them are subgroups in their own, and they are mutually like exclusive. None of their items are they are present in both sets. So essentially, both set of all in the even numbers and set of all odd numbers are cosets, and both of them will have the same number of items. That's also another important property that gives us Lagrange's theorem. So H here is like take n, which is a number of items in the whole group, and G is the number of is x or k, whatever it looks like, is the number of items in the subgroup. And the subgroup here is a coset. So Lagrange's theorem states that n is perfectly divisible by x, which which means that so n equal to this is m and x. Okay. So which means that set of n equal to mx means there's a finite number of cosets which together make up n. Here you can see that 6 is the order of the big group, that's the group here, and 2 is the order of the subgroup or coset. So here we can have exactly 3 number of cosets. 3 into 2 equal to 6. So since the no elements are overlapping there, it perfectly sums up. Let's just take 1, 2, 3, and then 4 and apply the same thing. 1 and 3 would be one coset. 2 and 4 would be another coset. And here the size is 4. Size of the coset here is 2. So hence there'll be only 2 cosets possible here. That is the intuition behind that. So next, again we'll go to back to the idea of group. We'll go to permutation groups, permutation groups, and symmetric groups. So okay. So what is a permutation group? So for example, again where is annotate? Yeah. Okay. So assume you have like a set which is 1, 2, and then 3. And you have a permutation here. The permutation here is a function that will convert the items in the set. So here both the domain and the range of the function are the same thing. So bijective map from A to A. So f of 1 gives 2. F of 2 gives 3. And f of 3 gives 1. So essentially it's a bijection within itself. So this is an example of a permutation. And so there'll be different kinds of permutation. P1 can be this. P2 can be in reverse order. So 1, 2, 3, 2, 2, 1, and then 3 to 2. Like this, you can have numerous number of permutation sets here. So these permutation sets, and there's also cyclic permutation set. So this one here is cyclic, since it follows 1 to 2, and then 2 to 3, and 3 to 1. This one here is also ironically cyclic in the reverse direction, because here it goes like this. Here it will go like from 1, it will go to 3, and then back. There can be non-cyclic permutation sets too. So next we'll go to a symmetric group. So just for symmetric group, this one will help. Yeah. Yeah. So here, like Udhaya's notes here. So symmetric group Sn is the set of all permutations of A. So here, oh, where did the annotations go? Okay, wait. Yes. So here P1 and P2 are two permutations. Like that, from the set, there can be total number of 6 permutations. So from the 6 permutation, we have P1, P2, P3, P4, P5, and P6. So a set which is made up of all these six as elements. So in this set, we won't have like integers or whole numbers as elements. We have matrices as elements. So in these kind of sets, it's called a symmetric group. So let's just go to order of sets. So order of sets means just the number of elements in a set. So here order of a symmetric group is n factorial. Since we have a permutation of everything and then we are combining all those. So order of Sn is n factorial. The question comes like order of what is the order of S3? Just write 3 factorial of the 1, 2, 3 that we saw. So again, what is Cayley's table? So Cayley's table is just a way of depicting and representing that. Annotation. Yeah. So Cayley's table. So here from left to right it goes. For example, this one equal to this row and then this column. That order. So what happens when both of these interact? So P1 is a permutation function. P1 O P2. O is the operation mentioned here. And this order means, so if you want to operate on anything, for example, X, the order should, this entry would be P1 of P2 of X. So here, despite P1 coming on right and P2 coming on left, P2 takes precedence here. So let's just take, for example, P1. So P1, it's 1 and 1. So let's just take the number 2, for example, and then find why P1 to P1 will get this the same thing here. So first, let's just apply P2 operation on 2. P2 here is 2. So P2 operation of 2 will give you 1. And then P1 then after that, P1 operation on 1 will give you 1. So as a result, the answer is 1. Similarly, for 2, let's just take for 2 we took and then for 1. So again, P2 of 1 will give you 2 and then 2 of 2 will give you 2. So essentially take any 1, 2, 3, apply P1, P2 first and then P1 after that, you'll get this thing. Yeah. Okay, so let's just go and look at this from the beginning and solve some problems and see how it goes. We already saw binary operation, addition, group. What is a group? Abelian group, semi-group, monoid. Okay, so just see how this solution works. You have to determine whether the set N where n belongs to R is a under addition is a group. So addition here is the operation. Just take closure. So 10n plus 10n will give you 20n. Again 20n is 10 into 2. So you just replace n with 2n, you'll get it under real number. So it's closed under addition. And here, since it's 10, regardless of 10 into 10, or which order add 10 plus 10 plus 10, or this order. It will again give you 30n. It's again a form of 10n. So essentially, its associated property is covered here. And then existence of identity. So identity here is 0. 0 is identity. And 0 is also part of the set since where do we go? N belongs to R. So 0 is also possible. N can also be 0. So 10n can also be 0 here. So let's just take this problem. Just a by 2n, where a belongs to z. Z means integers. And n greater than 0. Under addition forms a group. So for it to be a group, it should have closure, associativity, additivity, and inverse. So closure and associativity can be easily proved. So for identity to exist, you need to have a by 2n, 2 power n, plus e, we should give the same. So e should be 0. So 0 by here, a 0 by 2n should be a form of a by 2 power n. So since a can be all real numbers, identity element will be 0 by 2 power n. And for inverse, so a by 2 power n plus a inverse should be equal to 0. So a inverse should be minus a by 2 power n. And since the a and minus a both are under real numbers, inverse is also satisfied. Yeah, and in this form, we can use scaling table to find out where inverses are, identity operators are. For example, for you know that for addition, identity operator is 0. So let's just take for 2, where is 0 coming? And then you see 4. So 2 and 4 are 2's inverse is 4, and 4's inverse is 2 here. So like that, Cayley's table representation can be used to find identity and inverse easily. This is that symmetric group sum we saw here. The same sum. Essentially, giving this as a table helps you find out here. So P1 is P1. You can see that identity operator for this, with this you can find. Yeah. Well, let's just go to the next thing, which is combinatorics, which is some rules, those. Yeah, this is another thing for what can we infer from Cayley's table, like I mentioned just now. Yeah. So this so combinatorics is basically sum rules, product rules, inclusion-exclusion principle, pigeonhole principle, and permutation combinations, that equations. That's it. So it's a relatively small topic. So what is sum rules? So sum rules means mutually exclusive choices. That is, you can treat some rules as so you can treat some rules uh, as or operator. So let's just take that Chennai and Bangalore. Like there can be 3 ways to go from Chennai and Bangalore. So we don't, it's A union B is equal to A plus B here. So product rule is multiplication, that's AND. So product rule is required when we have to use sequential operations. For example, okay, how many combinations of a shirt and a pant can you wear? If you have 3 combinations of shirts and 4 combinations of pants, you just multiply both of them instead of adding them. Since you're doing both at the same time, you're not doing one without the other. So, again, inclusion exclusion principle is nothing but that A union B equal to A plus B minus A intersection B, that formula, and for 3 variables. So next is pigeonhole principle. So I don't know why it's called pigeonhole principle. The name does not really equate pigeons here, but what it says is, so assume we have like n number of items. We have like 5 bags, and each bag can only hold a certain number of items, but you have like 50 items. So how do you put 50 items in 5 bags? So for that, a basic rule is n by k. So that if you put 50 items in 5 bags, there has to be one bag with 50 by 5 greater than or equal to 50 by 5 items. So this square bracket is here for integer value. Does not remain a fraction. If this comes as like 5 by, take 5 objects and 2 boxes. 5 by 2 is 2.5. Be at least one box with greater than or equal to 3 items. That's just it. So pigeonhole principle is not that big. So again, permutations. So permutation means it has to be a specific order. Right. Annotations don't move with the screen. Okay. Clear annotations. Okay, so permutation order is important. Yeah. So in permutations, you can't have 1, 2, 3 and 1, 3, 2 are effectively two different things. They do not represent the same thing in permutation. But in combinations, they are effectively the same thing. So this is the only formula here. So for permutation, you have 3 of n, r. That is, you have like total number of 5 numbers, 1, 2, 3, 4, and 5, and 3 spaces. You only have 3 spaces where you can represent. So how can you represent n numbers in three spaces without repetition? The permutation formula for that is n factorial by n minus r factorial. If you want with repetition, it is just n power r. Reason of n power r is every place can be n. So it can be n into n into n till r. Here combination is without repetition. Same formula, C of n comma r is nothing but n factorial by r factorial into n minus r factorial. And if you want repetition there, repetition is allowed. As in, you can have the same object being there more than 2 times. So then it will be C of n plus r minus 1 comma r. This is just formula. Actually, if you just memorize these 4 formulas, the entire this part of the unit 3 will be very easy. Most of it comes from this formula. So, yeah. So again, there's a thing called like stars and bars. It's basically useful in solving sums. Right? Yeah, sums like inequality sums. For example, sums like this where find the number of non-negative integer solutions of the inequality x1, x2, x3, x4 lesser than or equal to 10. So the same here. If you want number of non-negative stars and bars essentially means that you have like you have like 5 stars. Let's just take. And you can only represent them in 3 boxes. So you have like 2 bars here. So you're dividing the entire space into 3 regions. 1, 2, 3. You have to represent 5 in 3. So how can you represent 5 in 3? That is the question. So solution for that is here n is the number of objects. N equal to 5 here. And k is the number of variables. K equal to 3. Yeah. So distribute n objects into k boxes using k minus 1 dividers. That is number of bars is k minus 1, which is 2. So the formula for that is, which is n plus k minus 1 by k minus 1. This bracket essentially means C of n formula. So this is C of n. So C of n comma r we are using here, right? So the n part here is the top and the r part here is the bottom. That will give you the solution. Yeah. And then for some cases, it will be like number of positive solutions is required. In this case, some of sums here should be like not greater than 0, but greater than 1. So in this case, the formula simply changes to n minus 1 to k minus 1. You have to give one item to each box first, and then apply stars and bars. As in, you can't have one box empty. Just a small example problem here. So x plus 1 x1 plus x2 plus x3 equal to 10. And these are the conditions. So how do you represent this? So you can't have a condition like this, x1 greater than 2, x1 greater than 3. You just replace for, if you want everything to be greater than 0, it will be more easy for you. Just keep as y1 is x1 minus 2, y2 is x2 minus 3, and then take y1 greater than 0 like that. So if you replace that, you get this, and you solve it. I'll just send this PDF in the group. Yeah. I'll just stop recording.